Hey everyone, today I really quickly want to go over the non-reconstruction condition for the broadcasting on trees problem. So just really quickly as a recap of our problem, we have some infinite B-ary tree, T, and that's going to look something like this. On this B-ary tree, we get some message at the root, and every time it goes down to one of its children, it goes through some Markov kernel where we can potentially add some kind of noise to it. So the problem is, given all of these at some layer distance d away from the root, can we reconstruct what the root's message actually was? So one way we can define that is the information, mutual information between, we'll call the root x row, the mutual information between the root and at some layer d either equal to 0, or does it approach 0, or is it greater than 0? The broadcasting problem on an infinite B-ary tree with b is greater than 1. We have root distribution is going to be pi, and we have our edge kernel. We're going to assume that pi is reversible, and if it's true that the KL contraction coefficient between pi and p, so our kernel, and if it is true that this value is less than 1, then this implies that the mutual information between the root and layer D approaches 0 as D approaches infinity. Yeah, and just really quickly, I'll define our layer D is just going to be U such that distance between U and rho is equal to D. All right, so how do we go about proving this? That is a good question, and that's why we're here today. So first of all, I'm just going to really quickly define what the contraction coefficient actually is. Equivalently, one other way to think about this is just that, remember the data processing inequality. Basically, we're trying to find some coefficient here that is as large as possible. Okay, so next page. First, consider every v in L1. We let LDV equal every node in LD such that V is an ancestor of U. So basically all the children of any of these nodes in layer 1. And we'll be making a recurrence based on that. So we'll do that by first making upper bound on the mutual information at layer D between that and the root. We can only lose information by going down from the root to the first layer. So basically just splitting up the sum between the root and layer D between each of these ancestors. For each of these terms, we can consider the Markov chain, and we can actually say this. Normally, the Markov chain would go the other direction, like this, because it's flowing down the tree. But remember, from our problem, we assumed that the measure is reversible, and therefore we can just reverse the Markov chain. Now that we have a Markov chain, we can actually do the strong data processing inequality. This is where the contraction coefficient comes in. And then, so data processing is the information between, I can use this thing, between this and this must be less than or equal to mutual information between this and this, because you can only lose information by going through that transition. You can't gain any information. At this point, we're going to use the stationarity of our measure, because reversibility implies stationarity, and this basically means since we have this, we can move our entire field of reference down a step. So we can move it down 1 by We start at our root going down to layer d minus 1, and then we actually move everything down by 1. So then we move down to distance d from the root and distance 1 from the root, which is what xv is talking about. The step that we're going to do here is we basically take this thing, replace it with this thing because that's the same, and now we get this contraction coefficient times this thing. And you'll notice this thing is the same as, I should have said D, comma V. This thing is the same as this thing, so we can replace it with this. And so putting this all together, we get contraction coefficient. I'll just write the B at the front. So this B is from our sum, then this thing is from our strong data processing inequality, and then I'll write triangle. Then this thing is from our triangle, and this is from triangle. Yeah, and now we have a little recurrence. So we have from the mutual information between the root and our layer D, and mutual information between the root and layer D minus 1. And if we apply that D times, become the mutual information between the root and the root, which this turns out to just be entropy of the root. Okay, bang. This is great. This is what's going to finish our theorem. So if we look at this thing, as d approaches infinity, if what's inside is less than 1, then we know our mutual information will be upper bounded by something that approaches 0. Therefore, our mutual information approaches 0. Therefore, the tree will be non-reconstructible. So if contraction coefficient times b is less than 1, then as d approaches 0, mutual information between the root and layer d also approaches 0, and this means it is non-reconstructible. And, oops, I should say d approaches infinity. And that is our entire proof. Thank you for listening.